Hi everyone, this is the second video of the 12th week when we will briefly discuss network inference and in particular the approaches for link prediction in network. So if you, on the slides, if you move to the first slide, which will serve as some introduction, is the slide says that what network inference try to do is to infer some missing nodes or links in a network that are either missing, hidden, questionable, and so on. And this can happen for a number of different reasons. First reason would be that any network that we usually study is just a sample of the true network. So we have some missing nodes or links due to sampling. Of course, your retrieval process can include some errors or you get some noise in your data and so on and so forth. So what we will try to infer is that some hidden missing structure of the network. And we can do that in a number of ways. For instance, using the structural information of our current network, maybe how different dynamical processes occur on the network, and so on and so forth. And out of different network inference approaches, probably the most famous approaches are those for predicting future links in our network. So we will, given a particular network, we will try to predict which links are likely to occur in the future. And this has many practical applications. For instance, on Facebook, future link prediction is basically recommendation of future friendships between users of Facebook, as you know from the app, where you have those people you may know. They are using network analysis techniques there to try to infer which links are likely to occur on Facebook, or which people on Facebook you are likely to connect with. Further on, if you take on Amazon network, when you have users and products, and you connect users to products if user has bought that product, predicting future links in that kind of network is basically again a problem of recommending products to users, products that they have not yet bought based on their historical information. Moving on, for instance, in protein-protein interaction networks, the interactions between the proteins actually have to be tested in the laboratory, so that the biologist then says that there is some interaction between two proteins. These experiments are, of course, very costly. They take a lot of time, so it makes sense to try to predict which interactions are more likely than the rest and test them in the laboratory. On the slide, you can see an example of such link prediction for some air transportation network of Europe. And on the left-hand side, you can see the true network. In the middle, you can see a network where some links have been removed and some random links have been added. And finally, on the right-hand side, you can see the reconstructed network where authors try to reason which links are missing or which links should not be there, but they are in the network. And this is from a very famous paper that you can read by Roger Guimera and Marta Sales Pardo. And if you remember the first challenge that we had, the 4 nights challenge, that actually came from Roger Guimera. Okay, so in the remaining, we will discuss different techniques for link prediction in network. As I said, that this is surely the most popular application of any network analysis techniques, and you will find a lot of papers on this topic. So the question that we're trying to answer are which links are likely to occur in our network in the future. And how can we predict these links? There are a number of different approaches that we have mostly already discussed throughout the course, that I have here categorized into 4 categories that are not actually disjoint. You will later see that many of the approaches can be put in different categories. So firstly, we can take our current network and try to predict future link based on local structure information in that network or local dynamics. So that for 2 nodes I and j, for which we would like to know whether it is likely that they will link in the future or not, we can, for instance, take into account their structural property, or more precisely their local neighborhood in the network, and try to do prediction based on that. The approaches that will go in this category, firstly, structural equivalence approaches. Remember, structural equivalence refer 2 nodes are structurally equivalent if they share exactly the same neighbors, or they share many common neighbors. So we're taking into account the neighborhood of 2 nodes and trying to predict whether the link will occur. Then there are topological overlap indices. If you remember, these approaches are basically a generalization of the clustering coefficient for nodes to links, and we have already discussed this when we talked about, I don't know, link bridging, community detection, and so on. Then further on, we can use some node similarity indices that try to say which 2 nodes are most similar, and then you assume that similar nodes are more likely to connect than dissimilar node. You can use an approaches that use some dynamics on network, but simply locally, just some local dynamics, and so on. So I will call this some local link prediction approaches. Then we can also talk about more global approaches that do not take into account only the neighborhood of nodes I and j, but also the entire structure of the network. One such approach would be regular equivalence. When you, if you remember, 2 nodes are regularly equivalent if their neighbors are also regularly equivalent. So in a way, you're taking into account the entire network. Similarly, different link analysis algorithms, for instance, PageRank, will also take into account the entire network, and based on the PageRank score of 2 nodes I and j, maybe you can predict the link between them. Next, the approaches for global link prediction would also be any clustering approach, any approach that try to group the nodes in a network in some reasonable clusters. So like, for instance, community detection approaches, block modeling approaches, and so on, maybe approaches for detecting core periphery structure, and so on. Next approach is based on some is based on some models of networks, and then you predict the links based on maximizing the likelihood of a particular model. If you remember, for instance, stochastic block models or stochastic hierarchical models, so there you can again infer some groups of nodes in a network, and then try to infer the links in order to maximize the likelihood of the model. So basically you're optimizing some criterion function. And finally, probably the oldest approaches are something called, let's call them probabilistic inference methods, some relational models, and so on, which are like statistical approaches that are nowadays not that popular in network science. This was very popular like 20 years ago, so I will skip this in the remaining slides. Okay, so as you will see in the remaining slides, most of the approaches that we will introduce for link prediction you already know from some other topic, but sometimes they will be slightly different than how we introduce them when we, for instance, discuss link bridging or community detection and so on. And the main difference is that when you try to predict whether there should be a link between nodes I and J, you primarily assume that currently there is no link between nodes I and J, because otherwise the problem would be trivial. So as you will later see, some of the formulas that we already saw before will now be slightly changed, taking into account the fact that we will only predict the probability of a link between nodes I and J if nodes I and J are currently not connected, which was different than in the case, for instance, link bridging methods, when we assume that I and J are connected in order to say something about the importance of that particular link. Okay, there is, out of the four categories that I have listed on the slide, there is another category of methods which are nowadays probably most popular also for predicting links and any other application of network science, and these are so-called node embedding methods, where in some way, taking the entire network, you try to embed nodes in the network into high-dimensional space based on their structural information. And usually assumption is that nodes that are in a way similar should be embedded close, somewhere close in this high-dimensional space. And then you can use this information basically saying that similar nodes are more likely to link to one another, so nodes that are close in the embedding space are likely to form the link. Since these approaches are a bit more involved, I will only briefly mention them in the next video. Okay, if we now move to the slides and slowly introduce a couple of classical, most popular link prediction approaches. So, first group of approaches will be based on the concept of equivalence, on the concept that nodes that are likely to connect, nodes that are similar, share a lot of common neighbors. So we are basically predicting the links based on structural equivalence. And as you remember from your homework, when you were already dealing with link prediction, what link prediction approaches try to do is devise some index that will have high values for pairs of nodes that are likely to connect and low values for the rest. And this will in all the slides be denoted with S sub ij. So this will be the value of likelihood of a link between nodes I to and j. And the most simple approach based on equivalence will simply be that nodes that share a lot of common neighbors are more likely to connect in the future than nodes that do not share any neighbors. This will probably work well in, say, social networks where, due to triadic closure, the connected triplets of nodes usually form a triangle somewhere in the future. So the simplest common neighbors index would be simply to taking the size of the intersection of the neighborhoods of I and j, and the value of the common neighbors, the number of the common neighbors, tell you something about how likely that link is to occur. Notice that, again, as I said before, we are assuming that I and j are currently not connected. So we don't have to correct for two different cases whether I and j are connected or not. Okay, when we talked about structural equivalence, we already said that this information where the number of common neighbors of two nodes I and j, it can be a bit misleading because it depends on the size of the neighborhoods of I and j, how many nodes they can, how many neighbors they can actually share. So we would like to normalize this value in some appropriate way. The simplest possible approach that we have already mentioned before will be a simple Jacquard index or Jacquard similarity of two sets here gamma I and gamma j, and instead of taking only their intersection or the size of the intersection, we normalize this by the sum of their union. So you get an index between 0 and 1, which will be higher for nodes that are more likely to connect under these assumptions. Then we also, when we discuss structural equivalence, we also mention cosine similarity between of the neighborhoods of two nodes. And if you remember, we came up with a simple formula that's basically said that the similarity is the size of the intersection of the neighborhood divided by the geometric mean of the sizes of the neighborhood. So the product of the degrees divided by the square root of the product of the degrees. And finally, a final approach that I would also put in this category would be the similarity index first proposed in the paper by Light and co-authors that we have also already discussed before. And remember that in this particular scenario, we are normalizing the size of the intersection of the neighborhoods divided by the expected size of the expected number of the common neighbors of nodes I and j when we fix their degrees, but otherwise the nodes are forming links completely at random. This is something that we call the configuration model. So the formula is written here in green, and notice that since with link prediction we only want to get high values for pairs of nodes that are likely to link, low values for pairs of nodes that are unlikely to link, this division by n, when n is the number of nodes, is actually irrelevant for our purposes because it is a constant and it does not depend on I and j. So I can simplify the formula so that I normalize the size of the intersection by simply taking the product of the degrees of the nodes. Okay, so we have introduced a couple of approaches that are based on equivalence, on sharing a lot of neighbors of the two nodes, and as you will later see from the results, you can expect that these approaches will give you relatively similar performance in real scenarios. So if one of these approaches will work well, also the rest are expected to work well because they are all based on the idea of common neighbors. Okay, if we move on to the next category of approaches that are kind of very similar to the ones that we saw on the previous slide, but I'm here calling them here approaches based on topological overlap. If you remember, this is a generalization of clustering coefficient of nodes to links. The first approach that I could also include on the previous slide is so-called Sorensen neighbors index. And if we go back here in the Salton cosine similarity, we are normalizing the size of the intersection by the geometric mean of the degrees of the nodes. Instead of taking the geometric mean, you could also take the arithmetic mean, which will be simply the sum of the degrees divided by 2.
Again, for the same reason as before, this division by 2 here is simply a constant. It will not, it's not important for our link prediction problem. So the normalization will be simply the sum of the degrees of the nodes. Now, if we move to the last approach on the slide, so-called Hub depressed index, is based on the idea that if a node has a high degree, it's more likely to share neighbors with some other node, simply for the fact because that node with high degree connects to many other nodes. To account for that, we can, instead of normalizing the size of the intersection by some mean or geometric or arithmetic mean, we could, for instance, take the maximum degree of the nodes I and j in the denominator. So that's why this is called Hub depressed index, because the value of the index for nodes I and j, if either of those nodes is a hub, so high degree node, will be depressed, will be lower, because it's more likely to share a common neighbor with a high degree node than with a low degree node. And of course, we can turn the things around. Instead of taking the maximum degree, we can also take the minimum degree. The value will still obviously be between 0 and 1. And if this one is called Hub depressing index, maybe we can call the second one as Hub promoted index. Okay. So we've seen a couple of approaches based on structural equivalence and a couple of approaches based on topological overlap. Notice that many of these approaches, at least some of these approaches, are basically based on some random graph or network model, like for instance the configuration model, if you remember the like similarity index. So an approach that estimates the probability of a link as it would be estimated in the case of the configuration model would then simply be the size of the intersection divided by the expected number of common neighbors in the configuration model, and we get rid of this division by n. So the same index that we already saw before. Now, going on, the scale-free structure of real networks is usually believed to be a consequence of so-called preferential attachment, so that nodes are more likely to link to high-degree nodes than to low-degree nodes. In order to develop an index based on this idea, you could simply take for the values of your index to be the product of the degrees of nodes I and j. If at least one of the degrees is super high, then this index will have a high value, because we are likely to link to high degree nodes, and if both nodes have a high degree, then the value is even higher. So we seen two random graph models, and finally the simplest random graph model, so-called the Erdos-Renyi model. How would that kind of model predict the links in the network? Under the Erdos-Renyi model, each link occurs with the same probability, which is simply the density of the network, or the average degree divided by n minus 1, which does not depend on nodes I and j. The probability of the link is the same for every pair of nodes I and j. So from that point of view, our index is basically predicting the same value for every pair of nodes, so basically some constant, which means that this index will obviously be useless in practical scenarios for predicting links, but I'm still including it here just to get a better idea how this network model indices work. And you could, of course, devise a different index based on any random graph model. For instance, I don't know, some hyperbolic models, some embedding models, and so things that we have not actually discussed in the course. Okay, if we move on to the next slide, here the slide try to predict the links in a network based on some simple dynamical processes on the network. And the first and the most famous one is so-called resource allocation index, whose rationale is as follows. Imagine that you have two nodes, I and j, which are again not connected, and assume that they, let's say, share some common neighbors. And let's denote this common neighbor on the top as x. Now, what is the rationale of the index is that assume that each node in a network, say node j, sends one unit of some resource, of some information or anything that this resource would refer to all of its neighbors. So I will send one unit of resource to its neighbor x. And what will then the neighbor x do is he will collect all these resources that were sent to him and equally distribute them among their neighbors. So this one unit of resource that was sent from j to x, a fraction of it will be sent from x further to y, and since x will send the same amount of resource to all of its neighbors, the amount that he will send to node I will be 1 divided by k sub x, where k sub x is the degree of node x. And based on this idea, you can estimate the probability of a link between nodes I and j based on the amount of resource that is being sent between I and j, or the amount of resource that comes from j to node I. And of course, the other way around. And this gives us the definition of this so-called resource allocation index. How it is computed, you sum through all common neighbors of nodes I and j, so here denoted by x, and for each you sum the reciprocal values of the degree of that node. So 1 divided by k sub x, as we have explained on the blackboard. And that kind of approach often works quite well. So it is again taking into account the common neighbors of the nodes, the number of common neighbors, but it also takes into the account the degrees of these common neighbors, because it is more likely to share a node to share a neighbor with a high degree than a neighbor with a low degree, just due to the number of links of that neighbor. Going on, in practice, when you look at the approaches that in some way are estimating the number of common neighbors of nodes I and j, usually the so-called Adami-Chadar index works the best. As you can see, the definition is exactly the same as for the resource allocation index. The only difference is that you do not sum 1 over the degree, but you sum 1 over the logarithm of the degree. Why would that make sense? Because we know that in most networks, in many networks, the degree distribution is distributed according to the power law, and if you want to suppress very high values of degrees, that will otherwise be 1 divided by, I don't know, 1,000,000, which will be practically 0, you can take the logarithm of the degree instead of taking the regular degree. This is a similar ad hoc solution to the fact that the degrees are distributed according to the power law, so that degrees can be very different from one another. And we have already seen this ad hoc solution, if you remember, when we discussed approaches on graphlets and approaches for measuring similarity or similarity between two networks or comparing two networks. And Natasha Perjul proposed a similar ad hoc solution, as was also proposed in the paper of Vlada Adamic and Adar. So this is another approach. And final approach that I want to mention here in the dynamic slide is based on PageRank or random walks with this restarts, personalized PageRank, walk rank, as we called it when we talked about node centrality measures and so on. So if you remember, in a PageRank, you can imagine that how the algorithm works is that you have a random walker going around a network, and from time to time that random walker also randomly jumps to some other part of a network. And the importance of the nodes, so PageRank score, will basically be the probability that at one particular point in time, the random walker will be in a particular node, or equivalently, the amount of time that a random walker spends in a particular node. How can we use this idea for link prediction is that instead of randomly jumping to a randomly selected node in this PageRank framework, when we randomly jump, we always randomly jump in one particular node. So basically you start at, say, node I, and you do some random exploration, and after some time you jump back to node I. And then again you do some random walk and jump back. And again some random walk and jump back. Basically, how you can see the values that you're going to get for other nodes, these values in a way correspond to similarity of this other node to our teleport root node I. So if we take the random walk equation and estimate the probability that you will be at one particular node, say node J, while we always jump, when we do a random jump, we always jump to node I, not to some random node, which I will here denote with this superscript. This will basically tell you the similarity of all other nodes J, to our particular node I. And based on this similarity, you can then estimate what is the probability of a link between nodes I and J. Notice that if I take the if I take this value, this is basically saying how similar node J is to node I. I can turn the things around and always be jumping to node J and estimate how much time I spend in node I, which will then tell me how similar node I is to our root node J. And since this formula is not symmetric, these values are not necessarily the same. Because imagine that you have a network like this. Here is my node I, and here is my node J. Notice that just from the picture, you can see that node J is very important from node I's perspective, because it's the closest node and so on. However, if you turn the things around, from the node J's perspective, the node I is probably not that important, but node J has also a lot of other neighbors here and so on. So in order to make a symmetric measure of link probability between nodes I and J, you have to take into account both of these two values. So we can, for instance, take their average. Or some other aggregation of these two values, and in that way we will get a symmetric measure. And as for the reasons that we already discussed before, this division by 2 here is just a constant, is the same for every pair of nodes in a network, and that's why we can ignore it. Here is our walk rank formula. So page rank formula with 3 stars when you are always jumping to a particular teleport node, here denoted by T. Based on these values, you can then come up with the index for the similarity of the nodes, which is basically the sum of these two probabilities. Yeah, and in contrast to the approaches that we have seen so far, this work rank similarity is quite computationally demanding, because you can have to run the page rank algorithm from each particular node, so that you're always jumping to one particular node. So since PageRank is roughly linear, you have to do it for each particular node, so your approach will be at least quadratic, which does not really scale well to large networks. But here I am showing you a couple of examples of approaches that are in some way based on some dynamical processes on a network. This can either be this recursor allocation idea, or it can be the random walk idea of PageRank, and so on and so forth. Next, if we move on, the last slide with approaches are some link prediction approaches based on clustering the nodes in a network, something that you have already investigated also in your homework. And we can devise the so-called community structure index of nodes I and J based on the communities detected by some popular community detection algorithm, like the Louvain algorithm, Infomap, Leiden, or anything else. And once you have detected the communities, the assumption would be that future links are more likely to appear within communities than between communities. And how could we then devise such an index? We would say that the probability of a link between nodes I and J, if they are in the same cluster, then we could say that the link is likely to occur. But in order to also take into account the size and the density of that cluster or that community, we estimate that the value of the index is basically the density in a particular community. So if nodes I and J are in the same community, then the value of your index is the number of links divided by the maximum possible number of links. And similarly, if you have two nodes in different communities, a community detection idea would say that there should be very few links between communities, or almost no links between communities. So in that case, we will give some very low value to those pairs of nodes, here denoted by -infinity, but you could take any negative value or 0 or something like that. Okay, in this idea, we are only talking about community structure, but there are many other group or cluster structures that appear in real networks. In general, this can all be detected by block models or stochastic block models. So let's assume that you apply a classical stochastic block model approach to your network. Then based on the blocks that you have, you can again estimate the probability of a link. In the case if nodes I and j are in the same cluster or in the same community, say, or anything else, then you will estimate the probability of the link simply to be the density of that community, as we have done before. But in contrast to before, we also give a non-zero value to pairs of nodes that are in different clusters, in different communities, and again, we estimate this value to be the density between these two clusters. So that kind of approach could then take into the account, let's say, communities that appear in some parts of the network, and also say some bipartite structures that appear in some other part of the network, or some core periphery structure that appears in the network, and so on. So this is the final slide of some classical link prediction approaches that were proposed in the literature, and there are a lot of surveys available online. Many of those are also linked from EU-Chilnica, and you can look at those surveys to get even more ideas or more indexes that you can use for link prediction. So in the remaining of this lecture, we will try to use these indices in a number of random graphs and real networks, and see which approaches perform well, which approaches do not perform well, and try to reason what is the case. So we will, as you have done in your homework, we will see the link prediction as a ranking problem. And how our framework will work is that we will take a particular network that we currently have and let large L denotes the links in that network. First, I will randomly sample some number of pairs of nodes that are not currently linked, because this will serve as negative examples for my prediction. So there is no link there, and I would expect that my link prediction index gives a low value to that pair of nodes, that the link should not occur there. Then, after we have sampled some unlinked pairs of nodes, we also remove some random, the same number of randomly selected links in the network. So pairs of nodes for which we know that the link occurred there, and this will serve as our positive examples. Now that we have our negative and positive examples, so pairs of nodes I and j, we can compute our link prediction index for each of these pairs of nodes. And what we would like is that, as shown here at the very bottom of the slide, is that our link prediction index will give high values for the pairs of nodes that are in L sub p, so pairs of nodes that actually were linked, say, in the future, and that our link prediction index will give some low values to pairs of nodes that did not link, that serve as our negative examples. And then, as you have done in your homework, you can compute the area under the curve, which will basically tell you what is the probability that you are able to distinguish between a link and an unlinked pair of nodes. But you could also take some simple Pearson or Spearman correlation coefficient to see how the values that you're going to get from your index correlate with ideal values that you would like to get. So zeros for no links and ones for the links. And this is basically the standard link prediction setting that people usually use in their papers, and that we will also use in the following slide. In practice, it is often you get more reliable results if you use so-called temporal link prediction setting. that actually try to take into the account the time evolution of the network. So since all our networks are growing in time, you can fix your network at some point of time and try to predict the links that are that will occur or did occur in the next time step. So why would this be relevant? Because then you are predicting future links only from historical information, not the other way around. Because in standard link prediction setting, you might also be predicting, say, historical friends or friendship types based on future friendship ties, which is of course unrealistic, and you can get misleading results. So how would this setting look like? Very similar. You take a network up to time t, and again, first you sample some number of unlinked pairs of nodes, which will serve as your negative examples. Then you take all the links that occurred in the next time step as your positive examples. So, and we remove those links from the network. So all links that appear after some time t. And at the end, we again compute this link prediction index for all these pairs of nodes. And in contrast to before, we will be predicting the future links only based on historical information and not the other way around, which is obviously unrealistic. Okay, so now that we have discussed different link prediction indices and highlighted how our evaluation framework will look like, I have 8 examples of different real networks and random graphs on which we will test these approaches and see whether our results are reasonable. And again, since this is a natural point to make a break, I will make a break here and continue in a minute. So see you in a minute.